Welcome to the presentation on Human from Blur, Human Pose Tracking from Blurry Images. In this study, we delve into the challenging task of estimating 3D human poses from substantially blurred images. Human motion blur is primarily influenced by factors such as exposure time and the speed of motion. Longer exposure times, especially in low light conditions, or rapid human movements can lead to pronounced motion blur in photographs or videos. This blur presents significant challenges when it comes to accurately estimating human poses. Imagine capturing a fast-moving footballer during a nighttime match or a dancer's swift turn under dim stage lighting. The resulting blur can obscure critical details, making traditional pose estimation methods less effective. Our work aims to address these challenges and is particularly beneficial in fields like sports analysis. For our pipeline, the primary inputs consist of a clean background image and images that capture the motion blur. This blur is a result of rapid human movements captured within the frame. To ensure that our pipeline effectively processes the images, we start by cropping both the images and the background to centralize the motion blur. In our pre-processing stage, we incorporate two pivotal models. First, we apply metro directly to the blurred image, obtaining a predicted mesh. This mesh is then fit into simple parameters through a registration process. The second model, BGMV2, is crucial for silhouette extraction and background matting. For BGMV2 to operate effectively, it requires both the foreground, which is the blurred image, and the background as inputs. Building upon our pre-processing, we use the extracted data as an initialization point for our next steps. We employ a differentiable renderer, which is adept at rendering both the foreground and a soft silhouette of the provided simple mesh. We utilize a polynomial set to drive the joint rotation and global translation of the simple model. An essential premise of our approach is the assumption that each blurred image can be decomposed into an average of a series of successive subframes. Leveraging the capabilities of the differentiable renderer, we generate these subframes, both for the foreground and the silhouette, and subsequently average them. We compute loss terms using the input blur in the initially extracted silhouette. Additionally, regularization terms are incorporated to refine our model. The optimization process employs the atom optimizer. To address the challenge of motion ambiguity, especially with a single blurred image input, we utilize a short temporal motion prior. This prior, trained on the amassed dataset and fixed during optimization, aids in calculating the loss and suppressing any aberrant motion outputs. The example of optimization result of each iteration is shown above. When dealing with multiple blur images, the challenge of ambiguity presents itself differently than with single-frame inputs. In this multi-frame context, the task becomes somewhat more straightforward. Our primary focus is to ensure consistency at the boundaries. Specifically, we ensure that the joint rotation and translation remain constant between the last subframe of the current blurred image and the first subframe of the subsequent blurred image. This continuity ensures a seamless transition and smooth motion representation across frames. We show our results in comparison with other methods for semi-real samples from our leveraged BAST++ dataset. Here are also the results from synthetic dataset. We present real sample analyses using 4 blurred frames as input. We compare our results with methods like AFB and bin. Furthermore, to extract human poses for subframes, we apply metro on their outputs. We present results derived exclusively from our synthetic dataset. What's unique here is that we showcase textured results, offering a deeper understanding of our method. We use 40 subframes for single-frame examples. In this example, the motion could be well retrieved, even with the wrong leg pose in initialization. For this example, our method reveals correct directions of the joint's rotation. But the range of motion is not accurate. The motion of the right hand is hard to track from this blurry input. The motion is accurately retrieved in this example. Our method depends on the initialization requiring both a feasible initial pose and a good background matting. Moreover, also as shown in previous slides, the output texture is coarse. Thank you for watching.